Lecture 26, Descriptive Main Group Chemistry, the Nonmetals, Groups 4 and 5. In the second part of our unit on descriptive chemistry, we're going to take a look at the chemistry of the nonmetals. Before we begin talking about different nonmetals, we're going to take a look at reviewing periodic properties. You might remember from Gen Chem 1 that those periodic properties are those properties that are directly related to the electron structure of the elements. And that the periodic properties trends only apply to main group elements. There are 4 periodic properties that are going to be important to us as we discuss the chemistry of the main group nonmetals. The first periodic property is the ionization energy, which is the energy required to remove the highest energy electron from an atom. In the periodic table, ionization energy increases as you move from left to right across a row, and it decreases from top to bottom down a group. Ionization energy is most directly related to an atom's ability to lose an electron and form a cation. The second periodic property is sort of the opposite of ionization energy. It's the electron affinity, which is related to the ability for an atom to gain electrons. Electron affinity also increases as you go from left to right across a row, and it decreases from top to bottom down a group. Electron affinity is a measure of an atom's ability to form anions by gaining electrons from other atoms. These two properties are more directly related to elements that form ionic compounds. The third periodic property is the atomic radius, which, as it sounds, is the radius of the atom. Atomic radius has an opposite trend from the other properties that we're going to look at. That is, that the atomic radius decreases as you move from left to right across a row, and it increases as you move from top to bottom down a group. Atomic radius is directly related to bond lengths, which we'll also take a look at in our study of the nonmetals. The final periodic property is electronegativity, which is a property related to an atom's pull for electrons when it's participating in a chemical bond. Electronegativity increases as you move from left to right across a row, and it decreases from top to bottom down a group. Now that we've reviewed some of the periodic properties, let's take a look at some general observations about the main group nonmetals. Here's an observation in a theme that we're going to take a look at throughout this unit. And that is that second row elements typically behave differently than other elements within that same group. Why is this? It turns out that second row elements, being at the very tops of their groups, tend to have higher electronegativities and smaller atomic radii than other elements in their group. There are a few consequences to this that we're going to explore in this unit. Second row nonmetals tend to easily form double and triple bonds with other elements and with themselves. This is because these elements have small atomic radii, meaning that the atoms can get very close together to facilitate the pi bonding or sideways overlap of p orbitals required to form double and triple bonds. Second row elements also tend to be much more electronegative than other group elements, as mentioned before. Here are some examples of how that manifests itself. If you look at the periodic table and study electronegativity values, we find that nitrogen, oxygen, and fluorine are the most electronegative elements within the periodic table. This has consequences on how these elements react with others. For example, oxygen and fluorine, being the most electronegative elements, tend to be very good oxidizing agents. And unless oxygen reacts with fluorine, this is how these elements react with other elements. They tend to oxidize them. Nitrogen is slightly less electronegative than oxygen and fluorine and behaves a little bit differently. Nitrogen is a pretty good oxidizing agent, but it has to have a pretty high oxidation state to do so. For example, many compounds containing the nitrate ion tend to be good oxidizing agents. This is because in nitrate, nitrogen has the highest oxidation state it can, which is +5. Being very electronegative and having a high oxidation state makes nitrogen and nitrate very, very reactive. And nitrates tend to be dangerous because of this. Compounds like nitric acid are very good oxidizers and tend to react very violently with other elements, which can be a safety hazard. Another thing to look at is oxidation state trends. We mentioned oxidation state when talking about nitrogen, so let's review what that is. Oxidation state is a fictitious charge that we assign to elements within compounds to help track whether or not elements are oxidized or reduced during a redox reaction. Different elements tend to have common oxidation states, which are given in this table to the right. This shows common oxidation states for the main group elements. We're going to again focus on the nonmetals. If we look at second row elements versus other elements within that same group, we find that the oxidation states tend to be different when comparing a second row element to even a third row element. Let's look at a couple of examples of this. If we look at the nitrogen group and look at nitrogen, we see that nitrogen has a variety of oxidation states ranging from -3 to +5. However, if we look at the other elements within the nitrogen row or nitrogen group, we find that those elements have less oxidation states available. For example, phosphorus only has the oxidation states of +5, +3, and -3. If we look at the next group over, which is the oxygen group, we see that oxygen only has negative oxidation states, -1 and -2. This is attributed to oxygen's high electronegativity. It's more likely going to take electrons from another element than give electrons to another element. If you look at sulfur directly below oxygen, you find that it has more oxidation states available to it, most of them being positive. This is due to sulfur's lower electronegativity, where sulfur can either, depending on the reaction, give electrons away, which is more likely, or take electrons. We can also look at fluorine, which only has one oxidation state, which is pretty unique, and that oxidation state is -1. This means that fluorine only ever gains electrons and never gives away electrons during a redox reaction. If we look at the element directly below fluorine, which is chlorine, there's many oxidation states available to chlorine, ranging from +7 to -1. We can look at some other trends in oxidation states. The highest oxidation state a main group element typically has, the most negative oxidation state that an element typically has is usually equal to the CAS group number -8. Remember that the CAS group number, which is the Roman numeral with an A next to it, tends to be the number of valence electrons an element has. For example, in group 6A, which is the oxygen group, the lowest oxidation state that those elements can have is 6 minus 8, or negative 2. And most of the elements, as you can see, have that oxidation state available to it. Now, the most positive oxidation state that an element can have is just simply its CAS group number. So for elements within this group 6A, the oxygen group, the highest oxidation state those elements can have is plus 6. You can see that, with the exception of oxygen, most elements within the group 6A have a plus 6 oxidation state, or can have an plus 6 oxidation state. Another trend in oxidation states is that figuring out the rest of the oxidation states is a little simple. Usually the oxidation states vary by increments of 2 between the highest oxidation state and the lowest oxidation state. For example, the highest oxidation state for sulfur is plus 6. To figure out the other oxidation states, you simply subtract 2 from 6 until you get to the lowest oxidation state, which is minus 2. This means that sulfur has oxidation states of plus 6, plus 4, 2, 0, and minus 2. Please note that you do not, and I repeat, do not need to worry about memorizing the oxidation states of the nonmetals. We're simply looking at them to look at how they relate to periodic trends. We're ready to move on to the second part of our lecture, where we take a look at some properties of main group elements. Again, the trend is that we're going to take a look at two elements within a group. The second row element, which again tends to behave differently due to its different periodic properties than other elements in their group, and the third row element as a comparison. The first group we're going to look at is group 4A, and we're going to focus on carbon and silicon. One thing you should know about group 4A elements in general is that they're on the interface between elements that gain electrons to form an octet and elements that lose electrons to gain an octet when participating in chemical reactions. This makes group 4A elements the most versatile elements in terms of chemical bonding. There are a variety of different elements or different compounds that exist that contain group 4A elements, and there's no bigger variety than those compounds that contain carbon. In fact, there's so many compounds that contain carbon that there's a whole area of chemistry devoted to them, and that is organic chemistry. Why is carbon so special? Mainly, carbon is special because it has a low atomic radius. This directly affects its bonding. Carbon atoms can get very close to one another. And because of this, carbon tends to form long chains with itself. We call this property catenation. Carbon can catenate, forming long chains in molecules. This is useful in biological molecules and polymers such as DNA. Carbon, also with a small atomic radius, tends to form multiple bonds. This adds to the variety of different compounds that carbon can form. In fact, there are more compounds that can be formed from carbon than from any other element in the periodic table combined. And that's pretty amazing. For us, we're going to look at the variety of bonding in carbon by looking at its allotropes. Allotropes are different forms of the same element. Carbon has 3 allotropes that we're going to take a look at. And we're going to look at how different they are from one another in terms of bonding. The first allotrope of carbon is the most common, and that's graphite. You might have looked at graphite in Gen Chem 1 when you did your lab on molecular modeling. And you might remember that graphite consists of sheets of carbon atoms. These carbon atoms are bound together in fused six-membered rings with a substructure of benzene, or C6H6. Each carbon in a graphite sheet is sp2 hybridized. One thing to notice about graphite is it's one of the nonmetals that's a pretty strong electrical conductor. The reason why is because there are conjugated double bonds, which is you're not able to really see in the picture there. But if you look at the picture on the bottom right-hand side of the slide, you'll see a picture of an extended pi system, where the p orbitals on each carbon that's in a graphite sheet fuse together to form one big pi bond that spreads out throughout the entire sheet. This allows electrons to move easily across the sheet, making graphite a very strong conductor. We know this because we've used graphite as electrodes in our electrochemistry unit. You should also know that a single sheet of graphite or graphene is very strong due to the multiple bonding that's there and that extended pi system. However, graphene sheets in graphite are only held together by London dispersion forces. Those are the weak forces that hold together different molecules due to their electron cloud distortions. Because graphite sheets are only held together by London dispersion forces, it is very easy to shave off a sheet of graphene from a graphite sample. This is why we use graphite in pencils. The second allotrope of carbon is diamond. The main difference between diamond and graphite is instead of having a system of conjugated double bonds, all of the atoms in diamond are singly bonded together, forming a very rigid structure. Each carbon is bonded to 4 other carbons in diamond, and each carbon is sp3 hybridized, having a tetrahedral shape around them. Basically, a sample of diamond is one big giant molecule because all carbon atoms in diamond are covalently bonded together. Diamond is formed under high pressure and temperature conditions, usually deep below the Earth's surface. One thing you'll notice that's different between graphite and diamond is that diamond has a higher density since all the atoms, due to the difference in bonding. Diamond is also an extremely hard material due to this high density and the strong bonding, and is also a good insulator of heat. The third allotrope of carbon is Buckminster fullerene, or C60. C60 molecules were discovered in 1985 by Smalley and Kroto. This was discovered in a mass spectrometry experiment where it was noticed that in a sample of soot, one of the masses that was noticed in that mass spectrometry experiment corresponded to C60. Buckminster fullerene has a cage-like structure and is shaped like a soccer ball. The most technical term for that is a truncated icosahedron. It's named after Buckminster Fuller, who invented the geodesic dome. Fullerenes, Buckminster fullerene is one of the first compounds discovered in a class of compounds named fullerenes, which are cage-like carbon compounds, as the ones shown in the bottom right. The existence of these led to the emergence of nanoscience or nanotechnology as a discipline. One thing to notice about Buckminster fullerene is actually that, which is hard to see in the picture there, is that there are also alternating double and single bonds. This is another allotrope that shows the ability of carbon to form multiple bonds with other carbon atoms. Now that we looked at carbon, let's take a look at the third row element within carbon's group, and that's silicon. Now, silicon has a lower electronegativity and also a larger atomic radius than carbon. This means that silicon atoms cannot get very close to one another enough to form double bonds. Therefore, silicon tends to form single bonds. And it also tends not to form bonds with itself. Silicon, however, is the second most abundant element in the Earth's crust, and typically combines with oxygen and other elements to form what are known as silicates. In a silicate, the main unit is the tetrahedral SiO4 unit, which has silicon bonded to four oxygen atoms in terms of single bonds. We can connect these SiO4 subunits together to form a variety of different silicate structures. We're going to take a look at a select few of these structures. The first type of structure we're going to look at are silicas. Silicas are covalent network solids. That means that the tetrahedral units are all covalently bonded to one another to form an extended crystalline structure. The formula unit for silicas is SiO2. And there are two major types of silicas. Quartz is the crystalline form of SiO2 and is shown in the picture in the table. If you want a less ordered structure, you can heat a material like sand up to a very high temperature and then cool it very quickly, which doesn't allow the atoms enough time to form an extended crystalline structure. And this results in forming glass, which is amorphous silica. The second type of silicate structure are orthosilicates. In orthosilicates, the SiO4 unit forms a single polyatomic ion, or silicate. The formula unit for an orthosilicate is SiO4 4-. A good example of orthosilicate is the gemstone garnet, which also contains iron and aluminum. The iron contributes to the color of garnet. Garnet is also your professor's birthstone, which is why it was chosen. The third type of silicate structure we're going to look at are amphiboles. Amphiboles have the SiO4 subunits in double chain-like configurations. This double chain structure makes amphiboles very fibrous in nature. An example of an compound containing amphiboles is asbestos. Looking at a microscopic picture of asbestos, you can see the fibrous structure. Asbestos used to be used as a building material, but has since been abandoned due to its carcinogenic nature. The final type of silicate structure are phyllosilicates. These are sheets of SiO4 subunits. This configuration makes phyllosilicates very flaky in nature. A good example of a phyllosilicate is talc and mica, which are powder-like or flaky-like substances. You might wonder, what do I need to know from this information? You should know the 4 types of silicate structures: silicas, orthosilicates, amphiboles, and phyllosilicates, and the main structural components of them. You do not need to know formula units. The final group we're going to look at in this lecture are group 5A elements, nitrogen and phosphorus. We'll first take a look at nitrogen, which again is the second row element and has properties a little bit different than the third row element. Remember that because nitrogen is a second row element, it has a higher electronegativity and smaller atomic radius. Due to this, nitrogen atoms can get very close together, forming N2 molecules that have a triple bond between them. Nitrogen, as N2 molecules, make up about 78% of the Earth's atmosphere. Because nitrogen forms triple bonds with itself, this makes nitrogen very hard to get to react. Nitrogen tends to be very inert and is used in chemistry when an inert environment is needed. Because of its high abundance in the Earth's atmosphere, it's cheaper to use nitrogen. This also creates a problem. Nitrogen is very prevalent in fertilizers. And one of the major problems of the turn of the century was to get nitrogen to use the high abundance of nitrogen to manufacture precursors to fertilizers. However, this problem was solved by using what's known as the Haber process, which was discovered by Fritz Haber in the 19-teens. The Haber process focuses on fixing nitrogen. This means we want to combine nitrogen with hydrogen to form ammonia, which is a precursor for making fertilizer products. The Haber process uses different tweaks to control the kinetics and thermodynamics of the reaction between nitrogen and hydrogen to make ammonia, in order to make the process to make the process yield more product. Let's take a look at those kinetic and thermodynamic tweaks. Let's first look at the kinetics. If we look at the Haber process reaction to form ammonia from nitrogen and hydrogen, we can look at all of the components above the arrow. These components are things you do not have to worry about memorizing, but you should know their purpose. They're catalysts. They help to make the rate of reaction a lot faster. How do they do that? First of all, they increase the surface area for the reaction to take place. The nitrogen and hydrogen molecules absorb to the surface of the catalyst in order to be in the right configurations to make ammonia. The catalyst also has more electron density, which also helps the nitrogen and hydrogen atoms to absorb to the surface of the catalyst itself. This helps the reaction to occur a lot more faster than if the molecules were left in the gas phase. So this is a way to kinetically increase the rate of reaction to form more products. Now let's take a look at thermodynamic controls. These controls are related to the equilibrium between the nitrogen and hydrogen and the product ammonia. We can explain those thermodynamic tweaks using Le Chatelier's principle, where we're using pressure and temperature to actually cause the equilibrium to shift towards more products. One thing you'll notice about the Haber process is that it takes place at very high pressures, at upwards of 200 atmospheres. If you recall, increasing the pressure of the reaction tends to shift the reaction towards shifts the equilibrium towards making less moles of gas. Since the products have less moles of gas, increasing the pressure will push the equilibrium towards making more ammonia. Another tweak we can try is temperature. The reaction between nitrogen and hydrogen to make ammonia is an exothermic reaction. So you would think that running the reaction at a low temperature would make the reaction form more product. However, in order to get the catalyst to work, to make the rate of reaction higher, we need the reaction to occur at high temperatures. So we sacrifice the temperature aspect of thermodynamics to make sure that the kinetics work right. Here's the take-home message here is that the Haber process helps to make it easier for nitrogen to react by using kinetics and thermodynamics. Fritz Haber's contribution to making fertilizer to feed the world's growing population earned him a Nobel Prize in the 1920s. You should know that this was pretty controversial, since Fritz Haber also made a contribution to chemical warfare during World War I. Let's take a look at phosphorus. So phosphorus is the third row element, and it behaves a little bit differently from nitrogen. Nitrogen is fairly unreactive unless you have special processes to make things easier. Phosphorus, having a larger atomic radius, tends to form singly bonded structures with other elements and with itself. This makes phosphorus more reactive than nitrogen. We can look at the allotropes of phosphorus just like we did for carbon. Phosphorus has two major allotropes that are much more reactive than nitrogen is. The most reactive allotrope of phosphorus is white phosphorus, or P4. White phosphorus contains tetrahedron P4 molecules. Why is this structure so reactive? Other than having the single bonds, we have another issue, and that is the bond angle between the phosphorus-phosphorus bonds. This bond angle is 60 degrees. It's important to note that the p orbitals that phosphorus uses to bond tend to have angles of 90 degrees. This 60-degree bond angle is therefore smaller than the angle between the p orbitals in phosphorus. This makes phosphorus P4 a very strained molecule. To alleviate that angle strain, phosphorus will react very violently, mainly with oxygen. White phosphorus is highly flammable, which is why in the picture it is stored under oil to keep it from reacting with the air. It's also very reactive towards moisture. The other allotrope of phosphorus, red phosphorus, is less reactive. In red phosphorus, the tetrahedral subunits are in a chain-like structure. This chain-like structure actually alleviates some of the angle strain, making it less reactive. Red phosphorus can be stored in air and is one of the components in match heads. When you strike a match, the red phosphorus is converted into white phosphorus, which ignites in air. In order to look at some of the differences in reactivity between phosphorus and nitrogen, we're going to take a look at some of the elements that nitrogen and phosphorus forms. Most elements tend to form compounds with hydrogen and with oxygen. So we'll look at the hydrides and oxides of nitrogen and phosphorus as a comparison. Let's first take a look at the hydrides. The simplest hydrides that nitrogen and phosphorus can form are NH3 or ammonia and PH3, which is phosphine. We know that ammonia is considered to be a weak base. So in aqueous solution, ammonia is basic. But what about phosphine? It turns out that phosphine has no acid-base properties. It does not behave as a base in aqueous solution. Why is this different? The difference comes in the way that bonds are formed and the hybridization of the atoms. And this has a lot to do with the atomic radius. Nitrogen is a smaller atom. Therefore, in ammonia, in order for there to be enough room for all of the bonds in the lone pair, the nitrogen atom undergoes hybridization. Remember that the angle between p orbitals in a nitrogen atom are 90 degrees. But when nitrogen combines with hydrogen to form ammonia, the angle is larger, 106.7 degrees. This indicates that the nitrogen atom is hybridized. However, for phosphorus, which is a bigger atom, phosphorus is a bigger atom than nitrogen, and you notice that the bond angles are 93 degrees, which is very close to the 90 degrees. The 90 degrees of p orbitals in a lone atom. This means that the phosphorus atom in phosphine is not hybridizing. How does this relate to the reactivity as a base for both of these compounds? The lone pair in nitrogen tends to sit in a hybrid orbital. And we know that the hybridization of nitrogen is sp3 hybridized. That means the orbital is 25% s orbital and 75% p orbital. This s character, this means that the lone pair in nitrogen is sitting in an orbital that has a lot of p character. What does that mean? P orbitals hold their electrons further away from the nucleus of the atom. This means that the lone pair nitrogen is further away from the nucleus and is therefore more reactive. It is more likely to take protons from other atoms as a Bronsted-Lowry base. How about phosphorus? Since the orbitals do not hybridize, and the p orbitals are used mainly for bonding, the lone pair for phosphorus is actually an s orbital. S orbitals hold their electrons more closely to the nucleus. This means that the lone pair on phosphorus is less reactive, and is less likely to take a proton from another element or another compound. Therefore, phosphine is not considered to be a basic compound. Let's take a look at now look at oxides of nitrogen and phosphorus. And mainly here, we're going to take a look at variety. Turns out that nitrogen, as you remember, has a lot of different oxidation states, meaning it's going to form a lot of different types of compounds with oxygen. There are several oxides of nitrogen that exist. There's N2O, or nitrous oxide, which has nitrogen in the +1 oxidation state. There's nitric oxide, which is NO, which has oxygen in the +2 oxidation state. N2O3, dinitrogen trioxide, which has oxygen in the +3 oxidation state. Nitrogen dioxide and dinitrogen tetroxide each have oxygen in the +4 oxidation state. And N2O5, dinitrogen pentoxide, has nitrogen in the +5 oxidation state. Again, please do not worry about memorizing all these different compounds of all these different oxides of nitrogen. Just realize that nitrogen has a variety of forms a variety of oxides due to the fact that it has several different oxidation states. However, if we look at phosphorus, there are only two principal oxides of phosphorus. There's tetraphosphorus hexoxide, P4O6, where phosphorus is in the +3 oxidation state, and tetraphosphorus decoxide, P4O10, where phosphorus is in the +5 oxidation state. I realize that we just went over a ton of information. And you might be wondering, what do I need to know from all this information? There will be a study guide related to this part of our unit that is separate from other study guides that you might receive. That you may receive for different exams. You should also note that this lecture represents the cutoff for an upcoming exam. Therefore, material that's covered after this exam will only appear after this lecture will only appear on the final. Okay, take care, guys.